Okay, next we have Heisenberg uncertainty principle. Heisenberg was a German scientist. He was a German scientist who in 1927 present this principle. Now, according to this principle, now this principle is only for microscopic particle, okay? Particles like electron, proton, neutron, etc. So this principle is only for these microscopic particles, and they are moving with a high speed, like with a speed which is approximately equal to the speed of light. Now, what is the basics of this principle? This principle says that if we have a microscopic particle which is moving in a particular direction with high speed, the speed is approximately equal to the speed of light. Then if a particle is moving with this speed, then it is difficult to it is impossible to calculate like the exact position. Let's say this is the position and the exact momentum. Let's say this is the momentum in the x direction. Then it is difficult to it is impossible to calculate the exact position and momentum of this small moving particle precisely and simultaneously. So at a time, at a particular position, we cannot calculate the exact position as well as the exact momentum of this particle at this particular point. So I can say that according to this principle, so here it is impossible to calculate the exact position and momentum of small moving particle precisely and accurately. Precisely and simultaneously, sorry. Like simultaneously and precisely, we cannot calculate the exact position and exact momentum of a small moving particle. This is what we call it, the Heisenberg uncertainty principle. Like according to this principle, if we try to measure the exact position, or location of this small moving particle, then we will face difficulty in calculating the momentum of the particle. So if we precisely calculate the moment position, like position is precisely calculated, then there will be an error in measuring the momentum. Momentum px. Like if we calculate the position precisely, then at the same time if we calculate the momentum, then there will be always be an error in calculating the momentum of the particle. So the uncertainty principle can also be defined as, so here we can also be defined it as like this. If we try it to measure the position of a microscopic particle we face difficulty in measuring the exact momentum. So if one quantity is precisely measured, then the other quantity can't be precisely measured. So if we measure the position of a particle precisely and accurately, then there will be an error in the momentum Tx. Now so it means that the error or the uncertainty. The uncertainty means the error in the measurement of position and momentum must be greater than or equal to the reduced Planck constant h bar. So it means that if we calculate the position and momentum, then there will always be an error in measuring the position and momentum, such that the product of the error in position as well as in momentum will always be greater than or equal to this reduced Planck constant. In other words, we can also define this uncertainty principle like if we measure the position of and momentum of a particle simultaneously, like at the same time we are going to calculate we are going to find the exact position as well as we are calculating the momentum, then what will happen? There will always be an error in measurement. Now there will be an error in the measurement of position. Similarly, there will be error in the measurement of momentum. Now if the error in measuring the position is small, like if we accurately measure the position, then the error in measuring momentum will be greater. So we cannot precisely and simultaneously accurately measure the momentum. But the product of the two errors, delta x into delta p, will always be greater than or equal to this reduced Planck constant h bar. H bar is basically h divided by 2. Now, as I already mentioned before that, in the case of localizing of wave, we already calculate a relation that the product delta x, delta k, where delta k is the width of the wave, it's the width, and delta x is the region where the particle occupy that region. Now their product is always is of the order of 1. Now we know that k is equal to this k, which is equal to 2 pi over lambda. So this means that delta k will be equal to 2 delta into 2 pi over lambda. Now let's suppose this is my equation 1 and this is my equation number 2. Now using equation 2 in equation 1, we have delta x into delta of 2 pi over lambda is of the order of 1, but we know that lambda is related to the momentum by this relation. Okay, I call it the x component of the momentum because the wave is represented by this one. So here the wavelength is this one, which is lambda x along x-axis. So if I put this value, let's suppose this is 3 and this is 4. If I use equation 4 and 3, then we get delta x into delta. Now we have 2 pi and we have 1 over lambda, which is equal to px over h from this relation. So from this relation I can say that 1 over lambda is equal to px over h, which is of the order of 1. Now here 2 pi and h, they are all constant, so I can bring it outside of this small difference. So we have delta x into, we have 2 pi over h, we have delta p of x, which is of the order of 1. Or we can say that delta x, I will bring this delta px and I bring this term to this side, which is equal to 1 over 2 pi over h. I can say that delta x, delta p of x is equal to h over 2 pi. So delta x, delta px is of the order of h over 2 pi. This is basically which is equal to h bar. This h over 2 pi is h bar. I can say that delta x, delta px is of the order of h bar. So here this is the error in measuring the position, and this represents the error in measuring the momentum. So the error in measuring the position as well as the momentum is of the order of h bar. So it means that if we measure position precisely and accurately, then the error in measuring the momentum will be greater. In other words, we can say that in measuring the position, the error in measuring the position is smaller, then the error in measuring the position will be bigger. But the two errors are such that their product will always be equal to or greater than h bar. So overall I can say that delta x, delta px is greater than or equal to h bar. Now this is only for the x component. Okay, the error in measuring the x position and x momentum is of the order of h bar. Similarly, delta y into delta py is also greater than or equal to h bar, and similarly delta z, delta pz is also greater than or equal to h bar. But we have another thing, which is delta x, delta py is equal to 0, because if we are measuring the x component of position accurately, then at the same time we can measure the y component of momentum accurately. So the error in measuring the x component or the x position and error in measuring the y component of the momentum, they are such that their product is always equal to 0. So it means that we can precisely and simultaneously measure the x position in one direction and momentum in on the other direction. Like if a particle, if we are going to measure the position x position and y component of the momentum, then we can simultaneously measure both these quantities precisely without any error. But if we are going to measure both the quantities in the same direction, like we are going to x component of x position and x momentum, then there will always be an error. and measuring the two quantities simultaneously. If we are measuring this quantity precisely, then we can't measure this quantity and that precision. And the measurement is such that the error in delta x and the error in delta px will always be greater than or equal to h bar. This is called Heisenberg uncertainty principle. Thank you.